Hello guys, welcome back to my channel. Today I'm going to be designing a step-down buck converter for typical microcontroller applications. For the input voltage, we are going to be using a USB port. So that has a voltage range of 4.75 volts to 5.25 volts. And we want to design the buck converter to provide 3.3 volts to a microcontroller. So what I'm going to be doing in this video is going from schematic capture, component selection to all the way through to PCB design and generating the manufacturing files. So let's get going. So let's start with the core component that we'll need for this part. I'm going to be using LM3670 as I've used this converter in the past and I know it works well. So LM3670 is a very small step down DC-DC converter for low voltage circuits. So this can be designed to provide you output voltages all the way down to 0.7 volts and at a maximum of 3.3 volts, which meets our requirements. One of the requirements I didn't define in the introduction was the current output requirement, which I'm going to be defining now. So what we need, or in this hypothetical scenario, what I need is to power a microcontroller which needs 0.05 or 50 milliamps. And then I have some op amps and some BJTs and some LEDs that will need an additional 150 milliamps. So we need a total current output of 200 milliamps. As you can see from the specification on the right hand side, this step down converter is able to provide an output current of 350 milliamps. So that will be suitable for our application. And we'll be able to evaluate what efficiencies we can achieve from the data sheet. So let's have a look at the data sheet of this component now. So on the screen on the right hand side, we have the data sheet for the port that we're using for the step down converter. This data sheet tells us the port has a very low quiescent current, which is the current just required to run the port itself, and can provide an output current capability of up to 350 milliamps, which meets our application very well, and has an input voltage range from 2.5 to 5.5 volts, which falls within our voltage input requirement range. Some of the nice things it tells us for the application, so battery powered devices, so that's very good. So we know, it's going to be low power consumption, and it's a buck converter anyway, which tend to be very efficient, so 85% plus efficiency. Looking at the port itself, we can see that it's a 5-pin port, and it comes in adjustable output variants as well as fixed output variants. We'll be using the fixed output variant today as we don't need to adjust the output voltage. We'll be going for 3.3 volts. So let's try and find the part number that we need to achieve that. One of the good things, I guess, in this specification, it gives you the different tolerances on your voltage output for the fixed voltage output. So we're interested in 3.3 volts, and we can see that we have a typical error of -2% to 4% when consuming 10 milliamps, and -6% to 4% when consuming up to 350 milliamps. I think for our application, that's going to be fine. However, we can calculate what our output voltage range is going to be. So 3.3 times 0.06, so that 6%. And we are going to take that away from the 3.3. So that gives us a lower input range of 3.102. And we can use the same formula to do the maximum calculation, however, changing the minus to a plus and changing the 6 to a 4, as that's the maximum error is 4%. At this point, you would want to make sure that the range that you have on this is suitable for your application. So let's say your microcontroller can only run up to 3.4 volts, then that might be a problem, as this regulator might provide you 3.42 volts output, which might damage the microcontroller. That's just as an example. I know most microcontrollers will typically be okay with this range, but it is application dependent. Let's see. So most data sheets for regulators will give you typical application circuits. And ideally, we want to start with that. So 5 volts to 3v3 volts is a very typical requirement. So there should be a design that we can follow from this data sheet. In the end, I will go through all of these calculations as well, but in the interest of just designing the part and keeping this simple, I'm just going to go through a application which we can just use. As we're going through the circuit design for this, let's start to build up a bill of materials for this part as well. So first of all, let's try and find the actual part number for the fixed voltage output 3v3 volts, which should be on this data sheet somewhere. So you can see from the packaging information that we have a part number that we need to order for the 3v3 voltage output, and it is called, so I'm going to write down the manufacturing part number on my bill of materials as LM3670 MF-3.3 NOPB. So that's no PB basically stands for no lead. So if you need something to be rush compliant, then you would want to find something without lead in there. I'm going to call this IC1 for our schematic capture later on. At this point, what you would want to do is make sure that this part is still in manufacture and is still available, easy to obtain. So you're not designing something that you find out later on that they've stopped making it or they've made the part obsolete. But in this design, I'm not really that concerned with it. I think the part is active or designated as active on the Texas Instrument website, and I'm fairly confident we'll be able to find this part. So let's start doing the component selection and schematic design. So on this page here of the datasheet for the buck regulator that we've selected, gives us a typical application for a fixed voltage output. So you can see from here that we will typically need one input capacitor, a inductor, and an output capacitor. This buck converter has an integrated switch, which means a MOSFET is built into the part, so we don't need to select one. We will go through these calculations at the end, so to ensure that we meet the part. However, the data sheet is telling us some typical parts that we can use. So for an inductor, so I'm just going to write down inductor here and write down so saturation current. We need 0.8 amps. As this is as this is given to us as in the typical circuit example, and an inductor value of 10 microhenries, and an inductor resistance we want to keep below 0.3 ohms to increase our efficiency of the part. Now the next part we're going to look at is the input capacitor. Now the datasheet tells us a ceramic input capacitor of 4.7 microfarads is sufficient for most applications. So I'm going to rely on the datasheet for now, and we can go through the calculations at the end. So I'm going to put down 4.7 microfarad capacitor and voltage rating. We don't expect this capacitor to see more than 5.25 volts. So I'm going to put down 10 volts as that's fairly easy to obtain. So we want a capacitor that has a voltage rating of at least 5.25 volts, but we're just going to step up to 10 volts. And it needs to be a ceramic capacitor, as they typically have low ESR, which is the equivalent series resistance. Another good thing about this data sheet, it gives you some inductors, part numbers, and things like that. However, for this design, we will go to Farnell or Musa or some other websites to select the component ourselves. I think it's good practice to try and select the components ourselves to make sure we're covering all the different parameters that we're interested in for the component itself. The next component that we're interested in is the output capacitor. Similar to before, I'm going to rely on the suggestions that are given in the datasheet. So for C out, the datasheet suggests that we use a 10 microfarad capacitor. So I'm going to put down 10 microfarads. And in terms of the voltage rating, similar to before, we only need 3.432 volts rating. However, I'm going to double that as capacitor voltage ratings do change with temperature and how much you load them as well. So what we need to do now, we are basically looking at the typical application circuit. We have the parameters that we need for the input capacitor, the output capacitor, and the inductor. So all the values are on here. Now we can go and select these components from Farnell and populate our bill of materials. So what I'm going to do is put down C in C1, make a note here that this is the input capacitor. C2 is the output capacitor. C in, we need a value of 4.7 microfarads, 10 volts minimum. And C out, we need 10 microfarads, 10 volts minimum. And inductor L1, we need an inductance value of 10 microhenries and a saturation current of at least 0.8 amps. Two parameters that I've missed out is ceramic and ceramic on the capacitors. I have accidentally put down the values in the manufacturing part number, so I'm just going to move them to here. So make a new column called value, put down LM3670 MF-3.3, 4.7 microfarads, 10 microfarads, and 10 microhenries. And then I'm going to make a description column as well to put down the other parameters that we're interested in. So 10 volt ceramic, 10 volt ceramic, and IS more than 0.8 amps. Some other things that we typically want on our bill of materials is the package. We already have the reference. We can also have a line number, which can be useful. So I'm going to put down line number 1, 2, 3, and 4. Let's now start selecting our components. I'm going to use Farnell for this, but you can use other websites if you want. There's Musa, there's DigiKey, various other websites that you can use online. So going on to Farnell, I'm going to start with the input capacitor selection. So in Farnell, you can go to basically to find a capacitor, use passive capacitor. You can just type in the value as well if you want to. We want a ceramic capacitor, and then we can start to populate these parts here. So the input capacitor, we need 4.7 microfarads. So we've got that selection there. And we need a minimum input voltage of 10 volts. So now I think we have filled in most of our parameters, but we can also, we selected ceramic capacitors anyway. So let's find available parts. You can see 4.7 microfarads is a very common value. So there are a lot of options out there. I'm going to go with something reasonably small. So you can see we have this part, which is 0805. So that's a good size to work with, and it's 20%. I quite like the look of this one because it's 10% X7R, which has a better performance over temperature. So I'm going to select this part and populate it in our bill of materials, and then put down a supplier and supply part number to make it easier to source when we come to actually build and manufacture the board. So our supplier for this part is Farnell, and the ordering number is 2496987. You can see, and the package is 0805. In Excel, if you want to start a number with 0, it's a good idea to put an apostrophe first, and then you can basically populate however you like as it turns it into text. So now we are going to select the 10 microfarad capacitor. So we want a minimum voltage of 10 volts and a capacitance value of 10 microfarads. So just looking for that, we can see we don't have any 10 microfarads, which is strange. There we go. So we got some 10 microfarad capacitor. I'm going to filter for that and see what the options are. If there are too many options, then I'll add in more filters. So the first one we selected was from a company called Wolfson. I'm going to look for X7R as they have better temperature characteristics, but I think X5R would be good as well. So most of these are good enough for what we need. I'm just going to go with a 10% one. As you know, there's a lot of options, so there's no harm in going for a slightly better spec. So this one here is 34p. So if you're optimizing for cost, obviously you might want to try and find the best costing options as well. So we can see the size on this capacitor is 1210. Let's see if we can find something smaller. So we've got a 14p capacitor here. It's 20% tolerance and X5R. So most of these are 10%, but so we got a nice 27 pence price 25 volts, 1206, 10%. So I'm going to go with this one. As they are ceramic capacitors, the ESR generally won't be a problem. But as before, so I'm going to write down the part number of the part of the component and then copy over the supplier, which in this case is 1L, and the supplier order number, which is 3416226. The last component that we need to select is the inductor. So let's do that now. So we need a 10 microhenry inductor. So we go passive, all products, passive, inductors. And we want fixed value inductors, where it might be a good idea to look at where most of the components are. So RF or power inductors might be good for us. We just need to make sure that we meet the saturation current. So we need a value of 10 microhenries. I was expecting more components to be 10 microhenries. Obviously, that's not the case. Let's see if there's anything we can find that's close. I like to go with components that have a lot of components available, as that will make it easier to swap out the components in the future, just in case they go obsolete or something like that. So we can see we've got 2,000, nearly 2,000 options for 10 microhenry component. So I'm just going to filter on that and see what we get. I'm going to go with power inductors. See what the ranges are on them. Maybe an RF inductor would be okay as well. I think for this design, I'm sticking with SMD, so I'll stick with that for now. If you don't find anything, then you can always swap over. So we have a saturation current here, and we want a minimum saturation current of, referencing back to our bill of materials, 800 milliamps. So I'm going to put down minimum saturation current of 800 milliamps and filter the results. You can see we only got 17 options now. So that narrows down our selection quite a bit. I quite like the look of this one. 800 milliamp saturation current, fairly decent price. There are some other options as well, but this one's fully shielded, so I think that's slightly better for emissions. Saying that, I like this one a little bit better because it's a company that I recognize. Um, let's have a look at the data sheet to see what the DC was. Oh, so we have the DC resistance over here. So that's 0.0136 ohms. Now, if you remember from the specification of the buck converter that we're using, the recommended the recommended maximum resistance of the inductor was 0.3 ohms. We can see over here that this component will be good, as the the DC resistance is 0.136, and it meets our saturation current. So I'm going to go into the component specification document, basically the data sheet for this component, and then have a look at the saturation current and make sure that's okay. So we're using a 10 microhenry part, so we're following this line over here. So we have a saturation current of 0.9 amps. So I think that will be good for us. And it's got a typical resistance, DC resistance of 0.119, and it's got maximum DC resistance of 0.136. Now this is the inductance value against frequency. So we know that our um, boost converter is going to operate roughly at 1 megahertz. So you can see over here that the inductance doesn't really change that much at this frequency. So we're good with that. And then this is the inductance versus the DC bias characteristics. And it's to do with the current on the left hand side, on the x-axis. We'll need to keep this data sheet for the footprint, as we might not have available on the PCB design package that we're going to use. So I'm fairly happy with this component. So I'm going to note down the component manufacturing part number, which is this, and 10 microhenries. I forgot to note down the package on this one, so I'll do that a bit later. On this one, the inductor case size, they're not generally very standardized. So we might need to just create that one ourselves and then put a reference to it here. But the Farnell order code for this part is 3416026. Now we have all the components that we need, and we can move on to the schematic capture. During the component selection, I neglected to select one of the USB-C connectors that we need for the design. So I'm going to go through Farnell again, looking for USB-C connectors, hopefully something at a reasonable price that we can use for the design. So you can see we've got a bunch of USB-C connectors. All I did was type in USB-C onto the search box, and I'm going to basically go to USB Type-C, filter on that so we get rid of all the micro connectors that we've got in the search, and go through a selection process. I'm just going to look for something fairly cheap. There will be slight differences in how the USB-C connector is mounted. So you can see there's 2 pins on this one, whereas the pin layout is slightly different on this connector here. And this is for the case. The pin layout for the actual data and power pins should be the same on all the connectors. So, I mean, this is a reasonably priced connector. I'm going to have a look at the data sheet. So, you've got USB-C with 2 prongs for the case, and then you'll have some pin layouts obviously internally for the data and signal. So this is perfect. We don't need USB 3.1 or anything. USB 2.1 is fine. Unfortunately, I cannot see a pinout on this data sheet, so that is a bit of a problem. And I can't also see a detailed drawing. So just going on to the parts page as a whole, you can see there are a few more documents, so we can have a look through this. So we have a drawing and a technical data sheet for the part. As you can see, there are a bunch of pins and the case mounting pins as well. And this gives us the footprint layout for the PCB. We'll make sure that our PCB follows this dimensions, and then this is the specification page. So I'm going to note down this part number and this Farnell order code on my bill of materials. Call this J1. So that is 3588205, and it's from Farnell. So I'm going to be using KiCAD or KiCAD to do the PCB design. So I'm going to draw out the circuit on there as well. So KiCAD, I've installed version 7, which is the latest version available to download as I'm making this video. So first things, I'm going to create a new project, and after creating the project in your preferred location, I'm going to open the schematic editor and just press OK on this option here. So first thing we want to do is try and look at the reference design that we have, which is basically this part here with the fixed voltage output. And we have part number there. So we've got obviously two capacitors and an inductor and the part itself. So I'm going to click on the component symbol here to add new components. The KiCAD will load the library, and this will be only for the first time. I would suggest you use the recommended option. It can take a while for KiCAD to load the library, so be patient. This only happens first time you open it. Subsequently, I think it'll be a lot faster to open up when you need to add in new components. So the first thing we need is two capacitors. So I'm just going to press C in the search option and put in our first capacitor and another capacitor. So just pressing that button again. So capacitor. Another thing we talked about was the fact that we're going to use a USB input to supply power to this board. So let's see if there are any USB connectors available. So obviously you can see that we have a lot of different USB connectors. We want a USB power only receptacle. So we can use this one here. So I've put down the USB connector, and obviously we got our two capacitors. So I'm going to edit the values to the values that we need. So we've got 4.7 microfarads for the input, and we have 10 microfarads for the output. We can see that we've got a ground here. So I'm going to draw some wires, and to draw the wires, you want to press W on your keyboard, or you can go to here and place wires. So first things, I'm going to connect the shield to the ground plane of the USB connector, and then I'm going to connect the two capacitors to the ground. Next, I'm going to connect 5 volts to the input capacitor and label that net using this option here, or you can press the L key on your keyboard. So pressing the L key, I want the net label to be power 5 volts, and this will make it easier for us to manage when we are doing the PCB design. So we'll be able to see P underscore 5 volts on the tracks that we're laying down. The next thing I want to do is basically see if I can find the component that we're using for the buck regulator, and if not, then we need to create the footprint or the schematic symbol. So LM3670. Looks like we have it, so we're quite lucky. We don't need to create it in this case. I'm going to put down the symbol here, connect up the ground plane, always referencing back to the reference design, making sure I'm not making any errors. We've got ground, pin 2. So pin 2 is going to ground. And then we have V in and enable going to the input voltage. So V in going to the input voltage and also enable. So you can see we have that connected. So for the tracks again, I'm pressing W. The next component that we need on this design is the inductor L1. So I'm going to click this symbol again. You can press the A key on your keyboard and L, search for L, which will give you the inductor symbol. To rotate components, you want to press the R key. So now just referencing back to the design, it's the reference design. We have pin number 5, which is called SW pin, going to an inductor. And after the inductor, we have a connection back to feedback and the output capacitor. So that's what we'll be replicating here. Pressing the W key, putting the wires down, and then connecting the feedback back to the inductor here. And then I'm going to note down the value of the inductor on this as 10 microhenries. So now basically we have most of our design ready, but we don't have any output connections. So what I'm going to do is find some output header pins, and basically this will allow us to connect to other ports, other circuits if we need to. Obviously, if you're following this reference, or if you're following this video for a design that you're doing on your own for some specific board, then you just want to carry on the 3v3 output to wherever you need it. So con, I'm just trying to find a connection on the list of symbols here. Looks like they've added a lot more components in here, which is really good. You don't have to design your own. So I've got to con. So I'm just going to use these pins as my output, but you can use whatever you like. So that's J1, and I'm going to copy that, and then also do a ground connection as well. So we have that connected. Again, for ease of PCB design, I'm going to label all these ports. So we've got P3V3. Then I'm going to add a label for feedback. And I'm going to add a label for the SW, so the switching node, which this is a quite an important node when doing buck converter designs. Just going to move it, make it in line. And then the last label I'm going to add is the ground, and I will put that on this node here. This is basically our schematic capture done. Just make sure that you have it correct with your reference design or whatever design you are following. And the next thing to do is to assign the footprints to these component symbols. And you can do that with the run footprint assignment tool on this button here. So we know for this part, we'll need to reference back to our bill of materials. So our 4.7 microfarad capacitor is the 0805. So I'm just selecting this one here, going to capacitors SMD and looking for the component that we need, so 0805. I'm thinking I'll order this board and build it, so I'm going to do hand solder, so I don't have to pay for soldering ups, and it'll be easier to build. But you can go for 0805, one that is not hand soldered, and you can still build them. The 0805 is a fairly big size anyway. The next component to look at is C2, which is the 10 microfarad capacitor, and that is 1206. And then I'm going to look at the USB-C receptacle, which hopefully I can find in here, otherwise I'll have to design my own. So I've got a few options here. I'm not sure what these are, but I'm going to just go with one of them for now and make sure that it looks okay when I come to the PCB design. And then for the two output pins, for the 3v3 and ground, I'm just going to go for a vertical socket pin. And this will give me the ability to put wires on there when I need to. I think inductors is going to be the most difficult one to find and put down. So obviously we have a part number. So in this case, it is a VLC. I'm just going to reference back to Parnell and see if we have this. So it's a TDK part. So we have some TDK options here, and we have some VLCP, VLF. However, I don't think we have what we need in terms of the size, so we might need to create one ourselves. What I'm going to do is choose one for now, and then change the component to suit my needs when doing the PCB design. But we can also create a new library to do this, and I will go through the process as well at the end. So I'm going to go for this one right now, and that basically means we have every single component selected. So I'm going to apply that, press OK, and that means now we can go on to do our PCB design. So I'm going to do Open PCB on board editor. Once you open the board editor or the PCB editor, what you need to do is basically update the PCB with changes made to the schematic. So obviously we added all those components. We need to bring those components in here. I mean, if you change the tracks or something like that, you would need to update the PCB every time you do that. So I'm going to do that here now and bring in all the bits from our design. We can see we have our connector, we have our inductor, we have our output pins. I'm going to roughly lay them out as we see them on the schematic. We have the input capacitor, which obviously is going to go near to the connector. We have our port here, and then we have the output capacitor. You can see I've put down all the parts that we see. It's generally a good idea to do it as per the schematic because generally that will work for the design that you're doing. So you've got two power pins in here. I'm not too familiar with the USB-C connections, so I'll need to do some research on that, but I'll make sure that all the output pins are okay. One thing I'm going to do is remove the feedback label to get the 3v3 label and just make it a bit easier for myself to read. So close that, remove this label as they are the same node. So it's prioritizing FB over this, and I'd rather see this on the PCB design. So what I'm going to do is open the board again and bring the changes back. So let's go and see the USB-C connections. Make sure that's all okay. So we have, this is looks like a good reference point to start with. We have, so I'm going to go back to our PCB design. So we have A12, which is ground. So look for A12 on here, which is ground. We have A9, which is weak bus power. We have B5, which is not really used for us, so should be unconnected, which it is. A5, which we're not using as well, so that's also unconnected. And then B9, which is VBus, so we have that connected. And we have B12, which I don't see on here, but I see over here, and it is ground pin basically. We don't need the A6 and A7 connections. If we were doing USB 2.0 with the USB-C connector, we would be using the middle 4 pins over here. So I'm happy with the connector. So I'm gonna just basically go on to do the design. So I want to put this component. I want to make this board as small as possible, obviously, but I'm not going to go overboard with the design. And to make the design a little bit easier, I'm going to remove the references and the values. So I'm going to get rid of the values, so that makes it a little bit easier to see. So we have J1 here, so I'm going to basically put that here. We have C1, we have U1. I'm going to bring the capacitor as close as possible. And then we have the inductor, which goes down here. Might be a good idea to move this at this point, as we need to have this connection going to this part here. And bring the whole thing closer and basically put some pins here. What I'm going to do now is define the edge of the board and basically make sure I try and stick inside it. But obviously, it's not that important for this design, as it is just a design that I'm doing for this video. So I'm just going to put this down here. If you want to see dimensions, you can basically use this dimensions tool here. So you see you've got this board size as 28.75 to 11.75. And if you want to see how this looks on a 3D layout, you can basically press Alt 3 and you'll see the board design, how it's going to look. So after selecting the USB connector, I've realized I need to go back and change the footprint to use the USB connector that I've selected. So the USB connector is a GCT USB 4105 16 pin. So I'm going to basically change the connector to that and apply that. I might need to go in and also change the USB-C receptacle to make sure that I have included everything that I need. But you can see that I'm using a USB-C receptacle with USB 2.0. I'm not going to be doing any communication anyway, so I think um, this one over here is okay. I'm just going to switch over to that. So I've changed the connector to USB 2.0 plug on the schematic. This is just to get the pin numbers correct. And then I'm going to update the PCB design to reflect the changes. So as you can see, I've got 5 volts coming on here, this pin here, and then I have ground and also 5 volts coming on this pin. Now that we have got the USB-C receptacle sorted out, one of the things that we need to do now is change the inductor design. So to do that, what you can do is basically create your own new library, which I'm going to show you how to do. Another thing you can do is also basically just go into this design footprint and change it. However, if you're going to reuse the components again and again, then you might as well create your library to um, suit what you need. So I'm going to go into basically KiCAD 7, and then you have this option here called Footprint Editor. So clicking on that, I will basically say New Library. I'm going to make a global library, and I will call that library My Engineering Experience Library. And then I will create in that one a new component, and I'm going to call that component the value from the inductor, as I don't have a footprint available for that inductor at the moment. So we know that the inductor was this one here. So what we're going to do is basically try and replicate this PCB LAN pattern that has been given to us. I don't think we need to have these uh, angled points, so we can just go ahead with a squared rectangle pads. So that's what I'll be doing. So it's, you can see the pad sizes are 3.9 by 1.6. So I'm going to put down 2 SMD pads. So you got pad 1 and pad 2, and then I will change the size on this pad to what we need. So that's the X is 3.9 and the Y is 1.6. I'll put that down here and then change this one up here. Um, that was 3.9 and 1.6. Now what we need to do is make sure that the pad is in the right place. So we need to get the separation right. So we can see that about the 0 point, they are 1.3 separated, the pads themselves. And basically what that tells us that the distance from the middle or the center here to the edge of the pad is 1.3 divided by 2. And um, the pad itself is 1.6. So 1.3, I'll just make a new Excel to do some quick calculations. That's 1.3 equals this divided by 2, and the pad itself is 1.6. So that divided by 2, if you add those together, that gives us the center location of this pad in the y direction is 1.45, and it's symmetrical, so this is minus 1.45 over here. So that's what I'll be doing next, making sure that the pads are in the center, in the X, so they are, and then this is 1.45 in this direction. So I'll change this to minus 1.45 and change this to plus 1.45. Now what I'll do is draw a courtyard or a silk screen around the component size. So this will help with the PCB design. So making sure we don't put any components too close to this. You can see the maximum size of the component is 4 by 4.3. So what I'll do is put in a silk screen of 4.3 around the component. So select the silk screen layer from here and go in the draw a rectangle. So I've got basically that. So the start point, I want -2 and end at 2 on the X, and Y, I want a square of 2, 2. You can see that this whole screen is going over the pad a little bit. So what I want, I don't quite like that. I'm going to make that size a little bit bigger. So I might go to 4.15, something like that. Sorry, 2.15 to cover the maximum dimension. And if it's still covering the pad, I'll just make it a little bit bigger on that dimension. So that is the Y. And in the Y side, I will just basically go 2.3 by 2.3, and that should be a good starting point for our component. Obviously, this is not perfect. You can put in a bunch of different um, layers on this to make the component as it should be. But for very basic circuits, I think this is good enough. So I'll save this. So we have this component in the library called My Electronic Engineering Library. So I will need to go back to the schematic design, run the footprint assignment tool again, and go into L1 and find my electronic engineering, engineering experience library, and select this component there. So I've basically, this is the new component I created on the PCB and add that in. For the USB plug, I will just go into the connectors, USB, and find the GCT connector over here. So that should be good enough. So apply and save schematic and continue, press OK. So then I will open the PCB design and import the changes. So you can see all the changes are on here. I've ended up with 2 connectors, but I can delete that. It's not a problem. And then basically I will put down the USB-C socket over here. So you've got the quad edge on this side. Connector called P1 in this case. So I'll put that down there. We have a capacitor. If you're going to be using some of these pins here, then obviously you wouldn't be able to put the component right next to it. So you might go something like this in your design. But for my design, I'm only using this board for power. So this should be good enough. So I'll bring the component closer and we can start on the PCB design. A good tip with the PCB design, especially for you using TI parts, is that there will be a reference or a guide on how you should design the PCB, and it'll tell you details about what you should avoid, how you should lay out the tracks and everything like that. So there is a layout example for this pad. So obviously you've got pin 1 there, pin 2, pin 3, 4 and 5. And you got your inductor, your input capacitor, somewhere here your output capacitor. Obviously we're not using the fixed value, we're not using the adjustable regulator, we're using the fixed value one, so we don't have these components. But if you're using the adjustable one, then you would also have them. So it tells you that you should have a copper track going from here to here, make it as thick as possible. They're using something called POR in PCB design, which basically just you design this little thing and it creates the track for you in that dimension rather than just putting down a track. So it says you want to have as many wires as possible between the top ground plane and the bottom ground plane. Obviously you got EN, which we're not using. So I'll be trying to follow this guideline on my PCB design as much as possible. So you've got connection from there to there, you've got this connection going back to re out, and obviously you've got your capacitor there. So let's get started with the PCB design. I think this is quite cool. So if you want to put in a pour, in KiCAD it's called the filled zone. So you press this button and you click where you want it, and then you select the net. So in our case, this is I'm doing it for SW. I'm going to select SW, put the pour down there, and if you press the B button, that will update this, and you can see that I've got it set as um, thermal relief, which I don't want because this is a SMD design. So I'm going to change that to solid. Hopefully that will all connect up. There we go. So we've got a nice thick copper or copper fill area over here. So going back to the example, we basically done this connection over here. Next, I'm going to do this connection. So you can see it's a thick copper core on the top side of where the component is. And that includes basically your capacitor pad and your inductor. I feel like I may have made a mistake on my schematic because I've got 3.3 there, so feedback. No, so I don't think I have because this is obviously an adjustable circuit design. But it's always good to obviously double check these things. But I'm on a fixed output voltage, so I'm connecting this pin directly to this point over here as it's given to us in the reference design. So this is the adjustable output where we've got R1 connection. You see, we are using this design where the inductor is connected directly to pin 4. So in our design, the inductor is connected directly to pin 4, and obviously it's connected to one of the capacitors. So what I'll do is create another port and put that down here. So P3V3, basically connect it up like this. I will bring the pin in later, but I want to sort out this design first, and then I can bring this pin down here somewhere and make sure that's all okay. So I've got a silk screen over here, so I'm going to put that as L1, make it nice and clear, so that when we come to build the board, it'll be easy. Another port that we need to do is 5 volts. So I'm going to go from there, put this pad down, go at an angle here, and basically I'm going to cover as much of this area as possible to get the 5-volt pin, and that should give us a nice solid connection. I'm not sure why it's not connecting to that, but we can try and fill that in manually. So what I'll do is just use a different track. Basically this is your copper tracks, and I'll just use one of them to make that connection from here down to here. Obviously I can make that a lot thicker. So I'll go in there, I'll basically press the E button to edit that track and change the width to 0.4, and that's nice and thick to reduce resistance of it. And the last thing that we want to do is basically connect up the enable pin. So obviously not a lot of power is running through there. So I might be able to basically just do this, and that might be okay. And then the last thing that we want to do is connect up the ground plane. To do this, obviously I'm going to use another port, and what I'm going to do is try and get everything in one go. We'll see how that works. If it doesn't work so well, we'll change some of it around and go from there. You see, I want to try and keep it to a 1-layer board, and that would be a little bit cheaper. But you can see that's covered it quite nicely. So we've got our ground covered here, we've got our ground covered here, we've got the ground covered there. I'm just going to put a track in just to make it certain. We've got our ground connected to this point. Again, I'm going to put down a track over here so that we don't get this weird connection on the pad. Change that to 0.4 like we did with the 5-volt line. And do the same thing over here. It doesn't matter where you take this track, as it's all going to be copper anyway. I'm just going to take it back to this point and change that to a 0.4 track, just to get rid of that curved edge on the pad, which can be problematic sometimes. So now referencing back to the example they gave us, obviously they had a ground plane which is kind of going underneath all the pads and everything. Obviously we haven't needed that in this design, so I'm just gonna avoid that. And one of the things that it tells you is to remove the ground plane around the switch node to avoid picking up switch noise. So you can see on our design, we have got a ground plane around here. So we will need to try and remove that. But before I do that, I'm just going to put down our connection points for the output of this board. So obviously we've got our 2 output pins. I'm going to bring this one in. Make sure they're connected so our edge of the board is not broken. So we got that all connected up. We got the two pins coming in. Now to remove a ground port from what we've done here, what we need to do is basically add in a clearance zone, so a keep out zone. So what we can do is from here, front copper, we're gonna keep out copper fills, and basically we can just go like this and update that. So that's obviously got rid of the copper track that was here. And you can see that it's also got rid of this copper track. So obviously we need to bring that back in. So I'm going to go over here, put this track back in and change that size to 0.4 again. I'm going to do the same thing over here to make that track a little bit neater. 0.4. And we also want to remove the ground plane from around this component as much as possible. So obviously we've got this pin and we'll need to keep that there obviously. We can potentially move it down, but what I'm going to do is just remove as much as possible, or as much as ground plane as possible. So I'll add in another zone around the component from here. So I'll keep out. So this keep out is basically keeping out everything. We only want to keep out um, the ground pour. So we'll see how that works for this. We're not using a pour on the switch node anyway, so that should be all right. As you can see, that's not affected the design. And I'll add in another keep out around here. What we also want to do is get rid of what we could have done from the start, I guess, is delete all these keep outs. So we don't need this one. We don't need this one. We don't need this one over here. What I'll do, I think this will make the design a lot easier or simpler, is move this ground plane. I want to, I think makes it easier to select. So move the ground plane to this side here, as we don't have many components there anyway. So we'll do basically this, and then we'll add in a few nodes over here. So to do that, you go to the place where you want to add a node, and you press insert. And then I want another one for this point here, and I want one more, so for this side over here. You can see that's going to create a nice track for us down to the ground connection. The design is saying to basically have this connection also included. So what I'm going to do is just take it from this side over here, and this is part of the USB-C connector. To make sure that's all connected properly, and then what I can do is basically expand this copper core over here to cover all of 3v3. Update that, and this means basically that we have a PCB design that is basically going to take in 5 volts from this USB-C connector over here and give us an output of 3 volts from here to here. So this is our ground point and our 3v3 output. We can look at this in the 3D viewer. to see. Obviously, this is a very simple design. So we got a nice USB-C connector here. We've got four components for the buck converters. We've got the buck converter itself. We've got a output capacitor, input capacitor, and an inductor. And then we've got two connection points for the output, so the ground and plus 3v3. So you can see from the 3D view that you can't tell which one's which. So what you can do is basically go to the silk screen and you can add in some text. So I'm going to write plus 3v3, put that down here, and then I'm going to add in more text called ground and put that down here. Now, if I go to the 3D viewer again, you can see that we've got 3v3 here, we've got ground here, so that will tell the person using the board, oh, that's where I need to make the connection. Basically, I'm happy with the design now. What I need to do is make sure that I'm not violating any rules or anything like that. Make sure all the copper tracks and everything are connected. So the way to do that is basically you go to the design rule checker window and you run a DRC. That's a design rule check, and it'll tell you if you've got any problems. So you got a clearance violation. Obviously, then you can decide if that's a problem for you or not, and you can check that against the place where you're gonna get the PCB manufactured from. Obviously, this hole here is from the USB-C connector itself, so there's not much we can do about it. And that's the same case with the other bits as well. So we can ignore those four. Then we have a rect on front sill screen. And the solder mask is basically clipped. Oh, so that's basically this this sill screen here is lying over the pad itself. So what I can do is basically go inside this component, edit footprint, edit library footprint. Something should come up soon, but oh, it's already open, that's why. So I'm going to go in here, press edit library footprint, load up the part, and what I want to do is basically expand these 2 points here to, let's say, 2.4, and that basically clears the two pads now. So if I save that and close this and update this, I might need to delete the component so it gets a new one. To rotate the part, you press the R button. And you can see now we should not have that warning anymore. So if I delete all markers and run DRC again, we've got rid of that warning that was on this pad. I can close that. I'm fairly happy with the design itself. Obviously, I've just messed around with the silk screen on the components. So I'll change that. The last thing that we need to do is create the manufacturing files. So to do that, you press this button over here. You select all the layers that you need to print. So in this case, obviously, we've got front and back copper. We don't need the back copper. It's empty anyway, but we can print that out. So what we can do is unselect it because we don't have any components. We just got the front copper, front paste, front silk screen, and front mask, and the edge of the board. And basically I will plot that and a generate drill file. So that does all the drill bits that we need. And that's it. I can basically go to a PCB design house. So let's say we use JLC PCB. And from my design files I can upload and they will give me a quote, hopefully, and they don't say that there's any issues. So you have the following files that we just created as the output files. And what I'm going to do is grab those and get a quote. So you got add Gerber files. I'm going to drop them in. It's not letting me select, so I'll try it a different way. So the YouTube videos, but converter design that we just did. Oh, it only supports, we need to zip the file first, so let's do that. So I've selected all the files on a different screen. I want to compress the zip file and then upload that. So now I'm uploading the zip file and let's see what it tells us. So it's processing the Gerber file. It'll give us a nice image of it, I think. We'll see what it looks like, what we're expecting it to look like. So we've got the top layer as basically the 5 volts coming in. We've got our 4 components. We've got the 3v3 output. We've got the ground connection. We've got the USB-C connector. And then the other side of the connector is blank. Obviously, it's a 1-layer board. It's selected it for us. You can select different standards and things if you need to. And the PCB build time calculated price obviously is still going through the calculations, but we've got all the different colors and options and things that we need to do basically. And we can see it's not thrown any issues with it yet. We don't need a stencil or anything. I think I will order this board, build it up for a YouTube video at a later date, and we can see if it works. I'm fairly confident that it will. So we've got a quote, $2 with a build time of 3 days. Obviously, it doesn't have a shipping estimate in there right now for 5 PCBs. I don't know how these guys do it. I forgot to record the audio in the original. So I'm happy with the PCB design now. I'm fairly confident it'll work. I'm going to try and build this board for another YouTube video. But I'll now go through all the calculations that we have on the datasheet of the LM3670. Make sure we're not falling foul of anything else. So stick around if you're interested in that. Hopefully this design was useful.